Hi, I'm Mike Hirschberg, the Executive Director of the Vertical Flight Society. Welcome to our 40th Annual Nikolsky Lecture. This live stream video is the first part of our 76th Annual Forum, which continues with our Grand Award Ceremony on this same YouTube channel in 2 hours, followed by the conference itself, which begins this coming Monday, October 5th. We hope that everyone can join us for the largest and longest-serving vertical flight technical event in the world. Each year, the Society's Alexander A. Nikolsky Honorary Lectureship is awarded to an individual who has a highly distinguished career in vertical flight aircraft research and development and is skilled at communicating their technical knowledge and experience. Although we can't be together in person today, we are pleased to host this lecture as a live stream to the whole world. Please type your comments into the YouTube chat window and preface a question you'd like us to pose to the speaker with a capital Q. VFS staff member Jim Sherman will moderate the questions at the end of the talk. This year's lecture is sponsored by GE Aviation. I've asked a member of our board of directors, Harry Nahadas, who is also the Vice President and General Manager of Turboshaft Engine Programs at GE Aviation, to introduce this year's Nikolsky lecturer. Harry?
Thanks, Mike. It's a great honor for me on behalf of the Vertical Flight Society and GE Aviation to introduce this year's Nikolsky Honorary Lecturer, Dr. Mark Tischler, Senior Technologist for Flight Control with the Combat Capabilities Development Center within the U.S. Army's Aviation and Missile Center. Dr. Tischler is recognized internationally as a leading authority on aircraft system identification, flight control, handling qualities, and simulation. He has led research, development, and implementation of analytical tools and methodologies that have fundamentally changed how aircraft flight control development and testing are conducted. His accomplishments reflect the abilities of a scientist who probes and discovers, and of an engineer who takes what is known and designs a product to meet a need. Mark received his BS and MS in aerospace engineering from the University of Maryland and a PhD from Stanford University. Following graduation from the University of Maryland in 1979, Mark worked at System Technology, Inc., and in 1983 became part of the Army Lab at Ames Research Center, Moffett Field, California, where he continues to work today in rotorcraft flight dynamics and control. Mark's accomplishments over the course of his career have been prodigious. The flight control methods and tools whose development he has led, Cipher and Conduit, have become standards in the technical community used at over 80 facilities worldwide. He has collaborated with industry on a multitude of major flight control development programs. Mark initiated a memorandum of agreement between the U.S. and Israel, which was awarded the Department of the Army's first ever International Collaboration Award. He has authored and co-authored over 200 research papers and was first author on 2 textbooks, Aircraft and Rotorcraft System Identification, published by the AIAA in 2006, updated in 2012, and Practical Methods for Aircraft and Rotorcraft Flight Control Design, published by the AIAA in 2017. For over 30 years, he has taught short courses on flight control, including at the Vertical Flight Society's annual forums, and has mentored an entire generation of flight control researchers. Mark is a technical fellow of the Vertical Flight Society and has received many other honors and awards, including twice receiving the Presidential Distinguished Rank Award, which is very impressive. With that, let me turn it over to Mark. The title of his lecture is Flight Control Technology Advancements and Challenges for Future Rotorcraft.
Thanks, Harry. It is a great pleasure to present my Nikolsky Lectureship this morning, and I thank the Society and the community for that. The CCDC Aviation and Missile Center has a mission to deliver collaborative and innovative capabilities to the warfighter. We are headquartered in Huntsville, Alabama, and I'm located on the campus of NASA Ames Research Center. We have a total strength of about 12,000 employees. Our priorities are readiness, the future force, and soldiers and people, and you'll see that our research is closely tied to these priorities. It is traditional to start the lecture with addressing the personal connections to Professor Nikolsky. And my personal connection is via Professor Pat Curtis, who was a student of Professor Nikolsky's, and he gave the 20th Nikolsky lecture, as well as developing the Princeton Long Track. Professor Curtis was a lifelong role model for me, a close mentor and research collaborator. He always stressed the importance of first principles, and is coined by my advisor at Stanford, Professor Art Bryson, a student of a student is a grand student, and that is my connection to Professor Nikolsky. This is an agenda for my presentation this morning. I'm going to start out talking about flight control drivers and technologies. There are many flight control drivers. I've only listed what I think are probably the top four. First is that the vehicle is inherently very high order. You have the 6 degrees of freedom of the fuselage, but also the degrees of freedom of the rotor, the inflow, the fuselage, sling loads, and so forth. This makes the system high order, and you need a high order linear model for flight control design and a high order nonlinear model for simulation. This requires engineers to have a strong multidisciplinary expertise. All hovering vehicles are unstable in hover and susceptible to turbulence, but this is especially true for multicopters. And finally, the bane of feedback control is time delays, and we're generating forces and moments via the rotor through about 100 milliseconds of time delay, which is dominated by the rotor flap, and it's the same time delay for RPM response. So this is on the left is a Bodie plot. You'll see a lot of these here. This is the roll response to lateral stick for the CH-53E data from Sikorsky. At low frequency, we have handling qualities and flight control. And at higher frequency here, you have the rotor and fuselage modes. But you can see that they're overlap, which means that they're going to interact when you have a flight control system. So you can see that more on the right-hand side, which is a model that I identified from flight test data for the BL-105. And you can see already that the body and the flapping response are coupled right here in this mode. But if we ignore the lead lag and time delays, the model indicates we can get the very high gains without going unstable. But in reality, when we include the lead lag and a relatively modest time delay of only 50 milliseconds, the lead lag mode will go unstable with feedback of the roll rate response. And this kind of conundrum it really limits flight control and dominates it, and was certainly the case for the command suite, for example. So we need accurate, higher order, nonlinear and linear models integrated in transparent development process to overcome these drivers. I'm going to focus on these four technical areas that have maintained a sustained focus in our team, as well as what I think are really the top, and I'm going to hit the top advancements for the last 50 years. I'm going to list many other, many folks, but try to hit what I think are the top achievements. So the first is handling qualities development, and there's a great Nikolsky lecture by Professor Patfield in 2012 for reference. So the first major advancement was ADS-33 as a breakthrough for rotorcraft. It came on the heels of a fixed wing update of 8785, the fixed wing spec, which was moved into the frequency domain because of the high levels of augmentation and feedback. And that kind of characterization works much better in the frequency domain. And that was also done for ADS-33. Another key advancement in ADS-33 was incorporation of mission task elements in which the pilot is asked to provide handling qualities ratings for specific maneuvers to cross-check the specs. We had many research partners internationally and nationally, and ADS-33 was released in 2000. There were flight test guides developed at the DLR as well as the Army, and ADS-33 has really been a breakthrough and provides guidance for flight control, design, development, and procurement. The first major breakthrough and concern was moving into the frequency domain, and there was concern about the applicability and practicality of this approach for rotorcraft. I had worked at System Technology where frequency sweeps had been developed and a lot of work on fixed wing. And I was the first to do frequency sweeps and system identification on a rotorcraft that being the XV-15. This was followed by a major flight test campaign at the Army's IFA Flight Test Center to demonstrate these methods on the Bell 214 ST. And here you can see the rolling response to lateral stick on the Bell 214. And this is the magnitude, phase, and coherence. The first thing you notice is the coherence is very high. which indicates that the overall closed loop system, including the flight control, is highly linear. The frequency response is shown in the solid line, and you can see a very low order model can be used to characterize the aircraft closed loop response in the dashed line. And this linear response, as you can see in the time domain, tracks the data very well, even over fairly large amplitudes of about 20 degrees per second. And so the frequency domain was adopted, and you need only the frequency responses, and the points are pulled off for the metrics in ADS-33. So this work demonstrated the safety and efficacy of the frequency domain, and a flight test manual instructing how to instrument the aircraft and conduct the tests was published by the Army in 1995. The next important advancement that I want to talk about is understanding the importance of time delays to handling qualities. This was well understood in the fixed wing community, and you can see results here from John Hodgkinson, and for time delays exceeding 120 milliseconds, the handling qualities ratings quickly degrade. The ADOX, which was the first production representative fly-by-wire, fly-by-light rotorcraft, had measured time delays. We did frequency sweeps on this aircraft, and I did the system identification. The ADOX has an identified time delay, as you can see here, of 240 milliseconds, which would predict very poor handling qualities for high gain tasks. And in fact, for the slope landing, and in this case, and run-on landings, the aircraft did enter into pilot-induced oscillations, or PIOs. And of course, these time delays have been improved over the years with improved technology. So there was also work going on in the UK at RAE, and you can see that they came up with a time delay cap of 200 milliseconds, and work done in collaboration with the DLR, and they came up with a time delay of 120 milliseconds, which matches the flight test results for the fixed wing perfectly, and that's no surprise, really. So while there in ADS-33B were allowable large values of time delay, a cap was put on the time delay of 120 milliseconds. And so large effective time delays are a key risk to fly-by-wire systems, both for handling qualities and feedback control, and the key contributors are the rotors, filters, actuator rate limiting is a major risk. The next area of advancement I want to focus on is the development of criteria for disturbance rejection. I developed the disturbance rejection bandwidth criteria in 2008. This is extracted by putting a frequency sweep into the hold variable. In this case, it's the roll angle response, and measuring the total frequency response. And this is really the sensitivity function. And you can see as you turn up the roll angle feedback gain, the DRB increases, and you can see in the time domain that results in the aircraft returning to trim faster. If you turn up the gains too high, eventually you're going to have a trade-off in the damping of the system, as you can see from this flight test data. When you conduct flight tests in the calm conditions, you get level 1 handling qualities even for very low DRBs. However, as soon as you encounter turbulence and winds, those same configurations produce level 2 handling qualities, and the pilots start to complain about the hold and trimability. And in order to improve handling qualities, you can see that you need to increase DRB, which drives to improve handling qualities ratings. Pilots talk about improved hold performance and trimability, as I mentioned. And then Dr. Tom Berger in 2016 worked with industry to develop a comprehensive database that was developed, and these validated DRB boundaries for attitude, velocity, and position. ADS-33 has been used on many aircraft. This is not an exhaustive list. Some programs in the US and internationally. And in fact, the first fly-by-wire helicopter designed to meet ADS-33 was the European NH-90. ADS-33 is a comprehensive, provides comprehensive design guidance to the flight control community, as well as flight control designers on many military and commercial rotorcraft programs. Even when these requirements are not explicitly required, they provide the guidance that the designers need. The first area that I want to focus on, the next area I want to focus on is physics-based simulation methods. I reference Pat Curtis's terrific Nikolsky lecture of 2000. The first models for flight control and simulation were tip path plane type models. And the pioneer in this area was Dr. Bob Chen at NASA with his development of the ARMCOP model. And this was a standard for many years for offline and piloted simulation. There are others, as I mentioned. And the next development was in the 1980s with blade element models. And the pioneer in this area was at Sikorsky, Mr. Jim Hallett, who developed the Genhel model there for the U-860. And for many other aircraft, the Genhel model has been a staple in the community as well as a standard for others. Initially, it was not real time, but as computational power improved, it became real time and now even includes flexible blades. But the early versions of Genhel, while they had all the higher order dynamics in the nonlinear simulation, the linearized simulation was 6 degrees of freedom. And as we've seen earlier, you need a higher order linear model. And the pioneer in this area was Dr. Dave Miller with his M97 model, which was the first higher order linear model for flight control design. And it was used at Boeing on ADOX, Comanche, and many other aircraft. I also want to highlight the development of the control equivalent turbulence model, or SETI, which provided deterministic turbulence that could be injected into the control system, and it made the aircraft move just like it does it made the aircraft move on a calm day, just like it does on a windy day. And this is extremely useful for ground-based simulation as well as in-flight simulation. And then finally, work at CAE Canada, where they coupled system identification with physics-based modeling to optimize and update the simulation input parameters. Since the 1990s, we've seen the incorporation of higher order aerodynamic models into physics-based modeling. And the first pioneer in this area was Professor Aviv Rosen from the Technion University in Israel, and his development of the Temora model, which was a prescribed vortex wake and demonstrated wake distortion associated with the angular rate of the tip path plane in inertial space. Now, there were two commercial simulation models that are widely used now. The first was by ART that I want to mention here. That's the Flight Lab model, and that can use either blade element arrow and now uses a vortex particle method, which is very close to CFD. A second commercial tool by CDI was the Charm free wake model, which is coupled, which can be coupled to flight dynamics codes. So even though we've come to a high level of sophistication in our aerodynamic modeling, there's always some uncertainty in the input parameters and limitations in the theory and how well it tracks the actual aircraft. And so there always requires a certain amount of flight test tuning to make the physics-based modeling agree with flight test data for use in flight control design. And an example of that is shown right here. This is a flight test data of the U-860, which was collected by NASA at the Ames Research Center. And you can see the dominant lead lag mode here and the flight dynamics low frequency. The initial baseline model, Genhel, had significant discrepancies due to inflow modeling at the time. And this was greatly improved with the incorporation of Professor Dave Peters' dynamic inflow model. And as that model was improved, the improvement with correlation with flight test data also improved, and you can see a analogous improvement in the time domain when the Pitt-Peters model was included. So system identification, therefore, provides a reliable method both for assessment of fidelity as well as calibrating improvements of the nonlinear model. This is going to be a common theme throughout my lecture. Ray Prouty in 1994 on Rotor and Wing published an article entitled "The Case of the Cross-Coupling Mystery," and he noted that all the models in the 1980s had the wrong sign in terms of the off-axis response. That is, for example, pitch response to a lateral input and roll response to longitudinal input, and it wasn't clear where this was coming from. A collaborative test between the Army and Sikorsky was conducted at full scale in the 40/80 wind tunnel of the Sikorsky Berlinus main rotor. And this was the first time that frequency sweeps were done in a wind tunnel for the use of system identification. You can see the test data here is shown in the solid line. And again, we have extremely high coherence, indicating that the rotor response is a highly linear system in terms of its overall dynamics. But the GenHel model has a very large discrepancies relative to the off-axis response, and this is the pitch response to the lateral stick. And you can see large discrepancies in magnitude and phase. You can couple the system identification with the flight test data, with the wind tunnel data, and update the physics-based parameters, things like the flap and lag modes and effective lock numbers and so forth, and drive the model to agree very well with test data. But the source of the physical error in those parameters was not known. And so that's where Professor Rosen came along and with Technion with his Temora model. It was a vortex wake model, and it demonstrated a distortion when the tip path plane entered into angular rates. And you can see that the vortices bunch up on one side and open up on the other. And this changes the cyclic inflow characteristics. And if we look, for example, at flight test data for the U-860, which was collected under our collaboration with Israel, you see the roll moment due to pitch rate. I conducted system identification here, and you can see that GenHel has the right magnitude and the opposite sign, whereas Temora is very close to the flight test value with the correct sign. This was not a closed form model, and so for that, two corrections were proposed. I proposed the aerodynamic phase lag correction, which you can see corrects the off-axis response. And there's a 180 degrees phase shift, which was indicating the wrong sign, as you can see, for GenHel. And then once that's updated, then it tracks very carefully. And then Jeff Keller, a student of Professor Curtis, and now at CDI, he developed the KR correction, which is widely used, and that's added on to the conventional Pitt-Peters model with the so-called KR correction. And the angular rate of the tip path plane in inertial space. And you can see that these two methods of correction essentially track each other and the flight test data very closely. The last area in physics-based modeling I want to talk about is stitch models from point model data and trim data. So this comes under the overall category of quasi-linear parameter varying models. It gives you a real-time model either from the higher order linear physics-based output or directly from system identification point models. And for rotorcraft, you only need about really 4 point models at low to mid altitude, and then much finer trim data. And these two quantities are stored in lookup tables as a function of forward airspeed. And then we have nonlinear gravity forces and nonlinear equations of motion. This gives a very accurate simulation of the dynamics and control of the aircraft. And what's really good about this type of model is that you only need to collect data for one mass configuration, and then it precisely extrapolates for mass properties as well as altitude and airspeed. And this was instantiated in a tool called Stitch and released by the Army in 2018. This is an example of the agreement for a known physics-based model, in this case GenHel, versus a Stitch model based on the higher order linear model output with a tool called Forecast. And you can see that the aircraft states are tracked the GenHel model perfectly. The overlay, you can't even see the difference between the curves. And again, in terms of the control variables, again, essentially perfectly. There's a very small bias here, but the dynamics are tracked extremely well. This approach was flight validated both in fixed wing and in rotary wing, as well as in advanced rotorcraft simulation, PSU. It's also the basis for developing level D training simulators, especially in Canada and in our NRC and CAE. And the approach is really ideal for simulation of UAVs, where physics-based model assumptions don't track the many UAV configurations all that well at the current time. It's also a very quick approach. Finally, I'd like to highlight ongoing work under the NATO AVT 296 entitled Rotorcraft Flight Simulation Model Fidelity Improvement and Assessment. There are a wide number of countries involved in this effort that I lead, as well as a very large database from legacy aircraft to advanced configurations and UAVs. We're developing methods for fidelity assessment as well as improvement methods, which range from simple to complex. There's a dedicated session next week in the VFS forum, as well as a final report that will be issued in this year in a lecture series at the beginning of next year. The third area I want to focus on is development of system identification, and a reference here is my textbook with the AAA in 2012. The early work in system identification is really to be credited to the fixed wing community, and the pioneers in this area were Iliff and Main from NASA and their development of maximum likelihood in the time domain. Rotorcraft came along very quickly, and the pioneer in this area is credited to Milusis at Sikorsky, and he adapted the fixed wing MMLE methods to rotorcraft. And one of his key breakthroughs was stressing the importance of the model structure. And in this case, he focused on the rotor body coupling and the need to include a system identification model structure, which includes rotor body coupling. And I showed you that at the beginning of my lecture, and this is all comes out of the work from Milusis. In the 1980s, there were significant advances. I developed the frequency response method and applied it to the XV-15. There was collaborative work with DLR, but the real breakthrough was a pioneering effort led by Dr. and Professor Peter Hamel from the DFELR, and that was a NATO activity under the AGAR working group rotorcraft system identification. Involved a large number of team members and research centers, and developed a landmark research report which showed the various system identification methods, compared them for 6 degree of freedom models is extracted from these 3 aircraft. The frequency response method I adapted from fixed wing from what I had learned in systems technology. I introduced some innovations, the use of a chirp Z transform, which shows an advanced FFT and provided improvements in resolution and accuracy, a multi-input, multi-output identification, and composite window averaging, which took a lot of the black magic out of selecting spectral windows. The next step is a parametric model and state space model identification. And here I developed a method for model structure determination and a way to identify physical parameters and incorporate those through complex constraints into the equations of motion. And finally, there's a time domain verification for dissimilar inputs. This was all instantiated in Cypher, and the advantages of this approach for flight control development rotorcraft is that it's applicable to unstable systems and for systems that have dynamics over a wide bandwidth. And most importantly, I think, is that the identification model is done using a Bodhi plot, so it's going to accurately track the Bodhi plot characteristics and ensure that when you do a flight control design, which also uses Bodhi plots, you're going to get the right stability margins and handling qualities characteristics, and all those metrics again are all extracted from Bodhi plots. And so Cypher was developed. Has a very user-friendly GUI, and was distributed in 1992. There are currently about 60 sites worldwide, and I've taught many training courses, and there are 2 textbooks. There's also outstanding work done by Susanna Weiss at the DLR in her development of FitLab, which has a range of identification methods, including a frequency response method, and that was released in 2016. This shows the flight test results from Bell Helicopter on the ARH, and you can see for the pitch response, very smooth quasi-steady characteristic, very high coherence, and the model tracks the flight test data essentially perfectly, as you can see, both in the frequency domain and the time domain. And again, I want to stress that the models that are tracked are not small perturbation models. This is, as you can see here, has an amplitude of plus or minus about 20 degrees per second, and there's a very large off-axis response, as you can see, and it tracks very well in the time domain. And finally, system identification was used to validate the control law implementation in the real-time flight control processors. So this was a 6 degree of freedom model, which basically has the assumption that of a quasi-steady response, and the rotor is modeled with a simple time delay. And this works quite well, provided an excellent basis for ARH flight control design and validation, and was a significant contributor to the reduction in overall planned flight test development time for this aircraft. As we've seen earlier, we need higher order models for modern aircraft. If we use a 6 degree of freedom model for the BO-105, as I showed earlier, it does not track data at all. It misses the coupled flap and fuselage dynamics, as you can see here, as well as lead lag dynamics. And so we needed to develop a higher order model. and I developed a hybrid rotor airframe model, which includes the first regressive rotor modes, as well as the engine modes. You can see that that tracks the flight test data extremely well. And a similar approach was used to extend fixed wing system identification model structures, and we conducted a collaborative flight test with Boeing. I developed a hybrid flexible model, and flight tests were conducted by the Army in cooperation with Boeing, and you can see here that you have the low frequency flight dynamics modes, but you also are well capturing the anti-symmetric wing bending modes. This was also extended in work in collaboration with Cessna Aircraft, Steve Haggard and his team, and this took a wind tunnel-based quasi-steady model, or so-called static elastic model, and then extended it with Nastran models for the first two bending modes. And you can see that the overall model tracks very well, and this is important for sensor placement in flexible aircraft. So the key applications here are flight control designed for modern rotorcraft, and especially for UAVs, which have all these higher order characteristics. I now want to move on to the fourth area, which is flight control systems. And here our reference is textbook developed that I led with our team at Ames Research Center and published by AAA in 2017. Again, the pioneering work was done in the fixed wing community, and this is a common theme you're hearing over and over again. And the first production digital fly-by-wire system, groundbreaking effort on the FAA team, was developed by McDonnell Douglas and fielded in 1978. Boeing came along and adapted these techniques to their heavy lift helicopter program and demonstrated them on flight testing of the Model 347 in 1975. And so this was really the first demonstration of digital fly-by-wire for rotorcraft, and it was very much ahead of its time. And it included advanced augmentation modes, feedback of the sling load motion to the control system to stabilize the damping and improve the damping of the sling load mode. And it had no mechanical backup, which is amazing for this time period. The Army extended this fly-by-wire work with the ARTI program in the 1980s. Included side stick controllers and advanced augmentation and flight test demonstration. The explicit model following approach was based on the pioneering work for helicopters in the collaboration between the U.S. and DFLR and Germany. It is essentially a 2 degree of freedom architecture. This shows an example of this architecture where you have a feedback loop which provides you stability and disturbance rejection. And that can be designed independently of the command model, which gives you piloted handling qualities in conjunction with ADS-33. Now, the ADOX, which I mentioned earlier, was the first production fly-by-wire or fly-by-light production representative demonstrator developed in the 1980s by Boeing. And it validated that explicit model following was really a key enabler of ADS-33 response types, and really enabled the simplified and transparent design and development of the flight control system, which also included things like a side stick controller with unique trim and pilot selectable outer loop modes. Since that time, explicit model following architectures have been widely adopted on modern fly-by-wire rotorcraft. The next area I want to focus on is the development of the design method using multi-objective parameter optimization. This is a specification-driven design, again, developed in the fixed wing community. And the key features of this approach is that the user just selects the architecture, and that can be a PID, explicit model following, or LQR and H infinity. And then you specify the design parameters like gains and weighting filters, for example. You specify which specifications you want to include from ADS-33 or 1797 for fixed wing. And the optimization then drives the design parameters to meet all the specifications. And you can generate what's called a Pareto front of optimized designs, which is a family of solutions which looks at the trade-off between improved performance versus improved control usage. And this approach was developed in Germany by the DFLR and used in development of the Eurofighter. It was adopted in the United States and advanced in pioneering work at the University of UC Berkeley, University of Maryland, and in collaboration with the UC San Luis Obispo. And all this work was done in collaboration with and led by the U.S. Army, and instantiated in the conduit package. This is a one-stop shop for flight control design, setup, optimization, and analysis. For example, it has libraries of all the specifications. You can just point and click and bring in any of the specifications you want. It has all the code necessary to run those specifications. And more importantly, by using ADS-33 boundaries, this takes care of the design scoring and weighting automatically. So the user doesn't have to worry about this. And the focus, therefore, is directly and correctly placed on selecting the requirements. So it's a requirements-driven approach with many applications to rotorcraft and fixed wing. It was distributed in 2001. There are about 50 sites worldwide. We've taught many training courses and mentioned our textbook in 2017. This is an example of this work led by NASA on the development in collaboration with Command Aerospace in the development of a control system for the unmanned KMAX. The barrier frame model was developed entirely from frequency sweeps done by Command, and we conducted system identification and extracted a stitch model for the aircraft. One of its major characteristics is that in hover, because of the low roll inertia, it has a very fast roll and stability. And time delays were estimated analytically and based on some benchtop data at a very low value of 95 milliseconds. And when the aircraft was taken to flight for the first time, it entered it immediately into oscillatory response. And so we went back and did system identification again to include the control system this time, and found that the real-time delay was about 290 milliseconds. And this is much closer to what we had seen just a little bit earlier on the ADOX program. And you can see that once the optimization was updated based on this improved model, you have a very good flight response with very good damping. So again, we see time delay is a key driver in fly-by-wire design, and it must be accurately determined and can only be accurately determined by system identification in the frequency domain. All the work so far has focused on full authority flight control systems. Legacy aircraft have partial authority, typically plus or minus 10%. And pioneering work was done by Dr. Sastre Budi at Sikorsky in collaboration with the U.S. Army on the MCLAWS program. And this was developed to achieve ADS-33 requirements and the partial authority to allow flight in the degraded visual environment. This work was advanced by incorporating a mechanical cancellation path, as you can see here, and that basically takes the mechanical path totally out of the system, as long as you stay within the 10% authority of the control system. And then that's replaced by an explicit model following system, as you can see here. And then Brian Fujisawa introduced outer loops in 2016. And this overall system was matured and integrated into the DVE mitigation program, along with advanced sensors and queuing, and allowed for deliberate missions in the DVE for legacy aircraft. Flight control is widely understood to be a fundamental technology layer for DVE operations. And this is some of Brian's test results conducted in a full-on brownout situation, which the pilot has almost no visibility in 2016 at the Yuma proving grounds. And you can see that the pilot handling qualities are level 2 in this case for just the SAS and FPS. This improves to borderline level 1, level 2 with just the inner loop. And then when you include outer loops such as position hold, you get a solid level 1 behavior with handling qualities ratings of HQR2s, which is really amazing in this condition. So the MCLAWS system provided improved piloting precision, greatly reduced workload, level 1 handling qualities, and DVE, all with a 10% authority system. I now want to talk about how these technologies have been used in integrated advanced example case studies. The first one is a partial authority system, and this is the CH-47 DAFIC system developed at Boeing. You see it here for the Chinook aircraft, and for the hover MTE, you see solid level 1 piloted performance, and the predicted quantitative ratings were expected to be level 1 based on ADS-33. And Chris Blanken at the Army, in conjunction with Army flight testing, conducted an operational test on the CH-47, and they demonstrated that for the legacy CH-47D aircraft, it took about 20 minutes to pick up a load on a moonless night, which is a DVE environment or degraded visual environment. But this reduced by an order of magnitude down to 2 minutes when you had level 1 handling qualities. This really shows the benefit of handling qualities to the operational mission. And the CH-47F DAFIX leveraged a lot of work done on the Comanche as well as the HAC program with things like tactile cueing and carefree maneuvering, as well as advanced test-tailored control laws. Boeing credited the use of the integrated technologies that we've talked about to meeting and maintaining the aggressive program goals. And the 47F DAFIX was field to theater with great improvements in safety. And this was credited by Boeing, especially in the DVE, to the use of ADS-33 methodologies and associated response types and control laws. The second success story I want to point out is the CH-53K program developed at Sikorsky. This modeling work was led by Dr. Sahastra Budi, and this was based on CH-53 system identification. And you can see the flight test data here at low frequency has the quasi-steady flight dynamics, but at higher frequency has the rotor modes and especially the flexible body modes, which were very important. And you can see that GenHill augmented with Nastran in a method very similar to what I demonstrated earlier, tracks the flight test data extremely closely and provided a basis for sensor placement, which is extremely important, and an excellent basis for flight control design. So the full authority CH-53K program had explicit model following with advanced modes, and especially advanced outer loop modes like deceleration to hover and position hold override. They used GenHill as shown here, as well as Conwood for the initial design efforts. It had an active stick and made a very strong use of the in-flight simulation capabilities of the Army and NRC for risk reduction. And preliminary flight test data indicates level 1 handling qualities, both for the nominal aircraft with the sling load and in the degraded visibility environment, UCE2. And they credited these advanced outer loop modes, really automated modes of deceleration to hover and position hold override, with providing for significant workload in the DVE. I now want to switch gears, take a breath, and move on to talk about how all these technologies are going to be applied to advanced configurations. And the first category that I want to talk about is the FLRAA and FARA configuration, some of them shown here. This is flight test data from the V280, and flight test data is shown here in the blue line, magnitude, phase, and coherence. Again, you see very high coherence, indicating very high precision and linearity of the input to output system. This is the bare airframe response, and sweeps were done on the aircraft and also in the nonlinear simulation in the system integration lab. And you see very good agreement both in magnitude and phase, and you can extract what's called the mismatched curve. Essentially is an error curve between these two sets of data, and you get this red line here, and that's within the proposed boundaries that were developed originally for fixed wing and adopted by the NATO working group. These are the so-called MUAD, or maximum unnoticeable added dynamic boundaries, and again, the V280 is well within those boundaries. There's also an integrated cost function based on system identification, and an integrated cost function of less than 100 is considered a good model. Less than 50 is considered a perfect model, and you can see that we're solidly in the good in the good region. And so we have a validated model for flight control design and handling qualities analysis in V280, and there's a paper on this next week by the authors. Another significant advancement in this category was a collaboration with Sikorsky on the X2, and frequency sweeps were conducted by Sikorsky, and system identification results here are shown in the blue line. Again, very, very high coherence. This was, we didn't know if this was going to be the case. It's a completely new aircraft, and yet again, very good, very strong linearity of the input to output process here. In this case, it's roll rate response to lateral stick. And we see here physics-based models, the GenHill model from Sikorsky, and the Helium model from the University of Maryland. and they agree with each other quite well, but you can see a considerable discrepancy, especially in the prediction of the lead lag modes. You can couple the identification with the flight test data and update the physics-based modeling, and this was work done by Dr. Juhas, and so the physics-based model parameters, things like the first bending mode and first lead lag mode, can be updated, and then the model very closely tracks the flight test data. So this is an approach to updating physics-based modeling. The overall result shows very good improvement in the correlation in both rotor dynamics as well as low frequency response, and you'll see more work on this again next week. Additional work was done in the incorporation of higher order aerodynamics, and this was pioneered under the U.S.-Israel collaboration, and using free wakes and validated using the UH-60 flight test data, and then it was adopted by ART and CDI and advanced. And at ART they incorporated the vortex particle method, and you can see the motion of the you could see the motion in the video of the wake response here, and then you collect the data, do system identification, and collect two essentially Peters inflow type models, but the parameters are updated, and then you get two linear models now that can be directly integrated into the flight lab flight dynamics model. And to see how well this agrees with the nonlinear data from the VPM method, we overlay here the time response for the rotor's self-induced inflow, as well as the interference inflow from the top to the bottom rotor, which is very large and almost as large as the self-induced inflow, as you can see. And this provides a real-time model, whereas the vortex particle method to generate this 90-second sweep takes about an hour. So it's not a real-time model, and it doesn't provide a higher order linearized capability as we can once we do the system identification. Then you can incorporate these models into Flight Lab, and you see extremely good agreement with the nonlinear behavior of the model, with a cost function of 24, which essentially is a perfect model, and we could have known that here. If we look at the original model based on Peters with no mutual interference, the cost function degrades by an order of magnitude. So this is a practical approach for state space identification of the inflow characteristics and development of a higher order state space model for flight control and real-time simulation. And the same approach has been used by CDI with their Charm free-wake model, and papers on both of these will be shown next week at the forum. The last area I want to highlight is development of advanced high-speed handling qualities and control laws. And this is work using generic high-speed configurations in collaboration with Penn State. And we had worked in collaboration with Cessna on their fixed-wing work in fly-by-wire. And in that work was demonstrated the advantages of advanced response type like NZ command, vertical acceleration command, and P beta control for lateral directional, neither of which are contained in ADS 33. But at high speed, they provide very good characteristics for the rotorcraft. And the reason is that at high speed, rotorcraft really fly like a wing. So the rotor becomes essentially a aspect ratio 1, and it becomes a circular wing. And therefore, at high speed, it's no surprise that that we would find that the fixed wing response types and fixed wing specs would be appropriate. Also developed here by Dr. Berger was advanced control allocation based on JSF work, as well as outer loop control for airspeed and flight path, which reduced workload. And you can see here the design process, which meets the 1797 requirements for fixed wing at high speed for these generic configurations. And in tests in the PSU fixed space simulator, borderline level 1 was extracted, and this improved to an HQR2 for some of the maneuvers when the outer loop mode was included, and this was found that needed to be pilot selectable. So this validated the approaches developed with fixed wing experience, as well as the outer loop control for high speed regime flight. Additional progress in flare and Farah configurations includes rotor state feedback, which improves hover hold and winds, and development of high-speed MTEs under the NRTC program. Chris Blanken at the U.S. Army published ADS-33 guidelines in a important publication in 2019, which essentially brings ADS-33 up to date for legacy aircraft. And finally, there's been a long-term collaboration with PySecchi under the ADAPT program, in which reliable damage tolerant control was developed for vehicles like compound aircraft, which have redundant actuators. But there still remains some key upcoming challenges, even with these, even with this progress. One is the development and publication of an ADS-33G for advanced configurations and associated MTEs. This is a challenge because of the proprietary nature of these programs and the need to publish the flight test results. And secondly, we need test facilities which are suited to parametric evaluation, parametric handling quality studies for these advanced high-speed configurations, and they do not yet exist except in ground-based simulation. The second upcoming challenge is a highly compressed development schedule that's anticipated for these programs, going right to a prototype, and the associated need to minimize flight test tuning. And in my view, overall, we are really at the 90% point. In my view, we have a very mature flight control technology for conventional single main rotor and tandem configurations. But we're really only at the starting gate for FEL type configurations. The next category of advanced configurations I want to talk about are the UAS and the urban air mobility configurations. In this case, based entirely on already flying unmanned versions of manned aircraft, as you can see some examples here. And one of these programs was the UAS MQ-8B Fire Scout. This was a collaboration with the Northrop Grumman, in which the model was entirely based on a stitched full flight envelope model from system identification. There was no physics-based modeling for flight control design. The ADS-33 and 9490 manned aircraft specs were used, and this is a kind of an eye chart, but it shows you the output from conduit and shows that all design points are in the white region, which is the level 1 region, and so it meets all level 1 characteristics. And Northrop Grumman had a very extensive hardware in the loop capability to both evaluate the hardware and do evaluation of the overall system for before flight testing. And finally, you can see very good agreement of the simulation environment with flight test data. And the MQ-8B Fire Scout was reached operational deployment on Navy ships in 2011. There have been additional progress highlights that I want to mention here. Additional work on the KMAX, and that used a full flight envelope stitch model for the operator training system. It used cable angle feedback for load stabilization, and there was also a work in this field done by U.S. Army and Stanford on the UH-60, and the KMAX reached a very successful 3-year operational trial in theater in the operational environment with thousands of deliveries to the forward operating bases, with over 4.5 million pounds of payload delivered. Additional progress highlights have been demonstration of ADS-33 as good guidance for full-scale UAS, as we've seen, and UAM on multiple programs, because these aircraft are full size, so it makes sense to use the full-size rotorcraft requirements. And then finally, there's been a lot of work in the area of autonomous guidance and navigation, and I mentioned U.S. Army here and CMU work in obstacle field navigation and safe landing area determination, as well as demonstration of dual lift, and in which 2 aircraft are collaborate to lift a load that's heavier than any one aircraft can lift by itself. But there still remains challenges. One of them is turbulence models, and for the shipboard and rooftop environments. The second is turbulence rejection characteristics, and then MTEs for the qualitative environment evaluation by the pilot. The next category of aircraft are eVTOL, and first I want to talk about are the small vehicles for imaging and surveillance. and these are both civilian and military configurations. These are just several of many, but you can see the key characteristic with it, which is true in all these vehicles, is that it has multiple rotors, and essentially for most of them, these are multi-copter configurations with mostly RPM control. Way at the University of Cincinnati was the first to apply frequency domain system identification to a quad rotor, and one of the key things that he demonstrated was the strong importance and dominance of the speed stability derivatives. So this is LV and MU that dominate for multicopters and hover while they're very, very small for flapping rotors. And this leads to a highly unstable bare airframe, and it also makes these aircraft extremely gust sensitive. So these are important challenges. Then Kenny Chung from NAMS, now USRA, and the U.S. Army had really a groundbreaking program, and Kenny led a program to demonstrate whether full-scale technologies could be applied to these to small scale, and in this case it was the IRIS Plus, and they demonstrated among many other things the importance of the rotor RPM in the flight dynamics. You can see here the extraction of a SETI model, a control equivalent turbulence input model. And again, this type of model allows you then to load in deterministic turbulence into the model. Again, this was groundbreaking work. And there was also flight control optimization conducted by Dr. Barrios and Dr. Juhas, and they demonstrated an improvement from the legacy flight control system down to the optimized system of an order of magnitude in terms of its hover hold capabilities. And Marcos also demonstrated strong correlation of this improvement and in the design process with disturbance rejection bandwidth. So that essentially validates the use of DRB in the flight control process going forward. There's also important work that's been done by Dr. Kirsty Ivler at the University of Portland, where her team developed methods to extract excellent models, and this for very large maneuvers, in this case 180 degrees per second. She also validated the use of Froude scaling, which had been around for subscale model testing in the fixed-wing community really since the 1920s on biplanes, and she validated this for two size hexacopters that varied by a scale factor of 2, and demonstrated that Froude scaling would bring the two models together. And that allows you to scale your identified model up and down to different vehicle sizes, as well as scale down the ADS-33 boundaries. And in this case, she demonstrated the Froude scaled level 1 DRB boundary that I showed you earlier tracks extremely well with flight test data that she collected. And you can see here level 1 behavior as soon as you cross this Froude scale boundary. There's additional work done by the U.S. Army in collaboration with UC Davis, Ron Hess, by Dr. Anthony Gong. And Anthony developed a stitch model from 3 point models that included the payload bay but were unloaded. And so the idea here is that I developed the stitch model, and you can see that agrees extremely well with the flight test data. And then he put a load inside of known mass properties. The stitch model extrapolates for those mass properties, and you can see it tracks extremely well with the flight test data. So this is the pitch rate response, and this is the AX response to longitudinal input. Again, very, very good agreement. And so the overall idea is that you have deterministic reconfiguration. You can take your payload, put it on a scale, measure its characteristics. Instantaneously, the stitch model updates to the off-nominal configurations. You get a new F and G matrix. And then you can use nonlinear dynamic inversion to update the control laws instantaneously, and you have automatic but deterministic reconfiguration for package delivery. Additional progress highlights that I want to mention are system identification work for multicopters, and this is led by Dr. Mark Lopez, and this demonstrated a significant loss of control power as the rotors start to come into interference with each other. And this has strong implications even in full scale. When you start to add a whole lot of rotors, they begin to interfere with each other, and control power is significantly reduced. They've Clyde, a system technology, has led a significant multi-year effort to develop a UAS handling qualities criteria, as well as mission task elements and a software toolbox. The Army has a program called JTARV, which is the Army's Joint Tactical Area Resupply Development Program. It includes both physics-based modeling as well as system identification and flight control performance. But yet again, with all these advances, there remains challenges. The multi-copters, as I mentioned, are all dominated by these stability derivatives, which makes them extremely sensitive to turbulence. And this has been demonstrated over and over again for these kind of vehicles. Flight-validated physics-based model simulation is really in the early stages, and it's not ready and does not track the flight test data based on theoretical values of the inputs. And also these configurations, they change rapidly. You fly them, you crash, you change the configuration the next day, you go out and fly again, and immediately you have to update your model and using system identification in this case, and you have to update your flight control feedback properties. And finally, there's a challenge to develop a full set of ADS-33 specs and associated MTEs. The last area of I want to focus on is very present and widely published urban air mobility programs. There are probably over 200 in the U.S. alone. This just shows several of them. But again, they're dominated by two things. First of all, that there are multiple control effectors. That some of them are multi-copters with RPM control, and also there are rotors that might be in close proximity to each other. And so there's been a lot of progress made. The initial flight tests have been reported in the popular literature for many unique configurations. ADS-33 has been demonstrated to be a good starting point for flight control design, but there remain some real significant challenges. First of all, there are very few technical details presented in the open literature for us to advance the state of the art. The configurations don't correspond with traditional rotorcraft simulation assumptions, and some pioneering work at NASA and RPI has demonstrated that as the vehicles get larger, the control power becomes limited with what you can get using RPM control, and there's a question as to whether you can actually get level 1 handling qualities with this type of control, or whether you need to go, whether you need to also incorporate a rotor collective. There's significant interference among the rotors, as we've demonstrated in subscale and with the aerodynamic surfaces. We also demonstrated this by the work done at CDI and ART. And also these configurations are highly overactuated, and so these configurations need optimal control allocation. And we need a validated damage tolerant control if we're going to operate these reliably and safely with passengers on board as in the UAM operational environment. So now I want to really take a step back and summarize the key challenges and what I think are the solution spaces for each one, and then wrap up my lecture. ADS-33 requirements are important, need to be developed for these advanced configurations. And in order to do that, we need publication of the flight test results of advanced configurations and parametric studies on relevant vehicles, flight vehicles, and simulation experiments. We need a validated flight dynamics and control models for physics-based modeling. And a way forward is to augment the physics-based modeling with these advanced higher order, higher fidelity aerodynamic models as demonstrated. We need turbulence models for a highly turbulent environment of either shipboard or rooftop operation, and the control equivalent turbulence input models can be used here and characterize CFD results in these environments. And we need careful modeling of high order dynamics and be sure that we get the time delays. This is essential for flight control and handling qualities. The third challenge has been the highly compressed development schedules. And for this, we need system identification, real-time stitch models, and I think a wider use of subscale demonstration, which is less expensive, and you can use fruit scaling to demonstrate flight control, flight dynamics, and flight control requirements. Finally, there are challenging flight control problems that can be tackled with multi-objective optimization and well-vetted control architectures like explicit model following. We need to adapt fixed wing requirements and knowledge to the high-speed flight regime, and control allocation and reallocation for damage tolerant control to these highly overactuated aircraft. So the methods, the simulation models, tools, and lessons learned over the past 30 years are really well suited, and they're the keys to success for the next generation of rotorcraft. I now want to take a final step back and a final breath to talk about lessons learned from my long career in flight control as an engineer and researcher. The first overwhelming lesson learned is the importance of collaboration, both with industry, internationally, with academia, to test a wide range of configurations, not only rotorcraft that the Army may be interested in, but also fixed-wing aircraft, and there are breakthroughs that are learned from fixed-wing aircraft and then can be applied to rotorcraft. And we see here legacy aircraft, collaboration with industry, and even UAVs like the Quantics. The second important lesson learned from my long career is the importance of providing integrated tools and documentation to the rotorcraft community. Gone long ago are the times when a researcher can develop an algorithm based on theory, apply it to their own test data, and publish that in a journal and say, okay, I'm done and I'm going to move on to the next project. Industry needs to have validated tools and methods. They need to be taught how to use these advanced tools in training courses and have strong documentation to validate these and learn from these. And we've done these with our range of tools in the Army. And there are, as I mentioned, also tools developed in Europe, for example, by DLR, training courses, and a forthcoming toolbox for the UAS development. And now some final lessons learned from my long career. First is I believe that we're in the golden age of flight control. There have been many new configurations now, many new missions, and many new challenges. And this really provides a golden opportunity for the young engineers coming into flight dynamics and control. Secondly, I have stressed the importance of flight control technology as a multidisciplinary model-based environment. And in order to achieve successful flight control, we need advanced and flight-validated methods and tools across a range of configurations, both rotary wing, fixed wing, and UAVs. And in order to get this broad range of configurations, again, we need collaboration. System identification is probably the single most important integrative and cost-saving flight control technology. Flight control technology advancement is highly nonlinear. You just can't plot breakthroughs on a Gantt chart. There are many lessons learned in cross-fertilization from the fixed-wing community that's been a key, as we've seen. And research is often ahead of its time. They may have been developed some time ago, placed on a shelf, and then picked up and applied to new applications. And then all of a sudden you have a breakthrough. And this cross-fertilization has been the key to breakthrough, not only in flight control, but in every other form of technology. Fielded applications of flight control research require sustained focus and is at least 5 to 10 years out in most cases. ADS-33, for example, took 20 years to develop. It is an invaluable tool, but it's been 20 years since the last update. And cipher and conduit methods and integrated software took 10 to 20 years to develop, and again, now are worldwide standards. Again, collaboration is the key. We need to interact with other researchers, with other cultures. This opens up new ways of thinking and new ways of problem solving. As Peter Hamel called them at the DLR, the aha moments that occur when you step away from your lab and you talk about the problems of the day over a beer with your collaborating partners. And finally, true technology transfer that changes practice takes a lot of effort. And this is going to be my overall message to you is in order to get flight validated methods to industry, you need those research papers, but you also need reliable software provided to the working level engineers. You need training courses. You need comprehensive textbooks and compendiums that demonstrate the lessons learned in a single resource. So overall, flight control advancement really requires, I believe, a focus on research flexibility, and it needs to be, I believe, more discovery driven as we go forward. And finally, some acknowledgements. I've had many mentors in my life. I've been blessed and fortunate with many mentors over the years. Some of them, many of them are in the audience, and some of them unfortunately have passed away. But I want to and I want to especially speak in this slide to the young engineers and say you really need to look out for mentors, folks that have taken the flight control path in the past that can steer both your research as well as your career decisions. And all of these people have had a large hand in my life and my career. And I really want to focus on my dad. My dad, for many of you that don't know, Mars Tischler was the inventor of the first transistorized heart pacemaker. He delivered it at the White House to President Eisenhower's cardiologist because President Eisenhower had a serious heart condition. And my dad was a visionary, and he could see where things needed to go. And he always emphasized to me as a young kid the need to stick by your guns, focus on the vision in the long term, and put in 100 and even 110% effort. And if your efforts pay off, you have to stay focused and get to the finish line. And that was the key message of my dad. And with that, I want to say that aeronautics has been my greatest passion since I was 12 years old, and I convinced my parents to buy me a model rocket set. And since then, I've been hooked on aeronautics. And I want to thank the vertical flight community for this wonderful honor to present the 40th Nikolsky Lecture and join a long list of my role models, many of whom have presented the lecture before me. Thank you very much, and I'm glad to take some questions at this time. Absolutely, absolutely. The community has greatly benefited from the work of the HS Now BFS. Yes. No, I can hear you. We can hear you just fine. Okay.
Not showing up. So now can you hear me on the live stream? All right, we're going to give it just a little more volume, maybe a little bit more over here too. So let me go back and restate what I said earlier. Dr. Tischler, thank you so much for your inspiring Nikolsky lecture and for your lifetime of contributions to our technical community. Just as you mentioned, collaboration throughout the end, especially the end of your presentation there. I just want to point out that Vertical Flight Society, that's really what we do. We bring together the academic and the industry and the government organizations and around the globe to collaborate and advance vertical flight. So with that, I want to thank you for all your efforts in bringing those resources together as well. And I'm going to moderate a few questions here. We actually got several questions that came in.
And especially I like to invite questions from some of my mentors in the fixed wing, rotor wing, flight control community. If you have any thoughts or questions, I'd love to hear from you.
All right. So, well, let's start with the first question that we have here, and this came quite a bit ago in your presentation, pretty close to the beginning. It says, it appears that there was a significant international collaboration during development. And has this technique been adopted broadly in the international community for this application? And I'll be honest, that was very, very early in the presentation, so I'm not exactly certain what he's referring to.
So, and the answer to that is yes. Collaboration has seen wide use. We have the NATO working groups right now under the RTO research collaboration. In Europe, they have collaborative activities, and we have our binational collaborations with France, Germany, and Israel. And in terms of adoption of the techniques and methodologies, Yes, ADS-33, as I mentioned, has been widely adopted as well as our system identification, flight control methods, all I highlighted throughout this presentation, and all widely used in the international community. Courses attended by the international audience, and so yes, this approach, it's really gratifying to me at this point in my career to see so many papers in the VFS that are using our techniques that we were involved in collaborating and developing and advancing.
Excellent. Thank you, sir. So the next question that came at about the same time was, should cipher/conduit, or I should say maybe cipher/conduit, be used as a flight test precursor to avoid problem harmonics, and what would be required for this implementation?
Well, conduit works either on physics-based models, which you have before the initial flight tests, as well as when you update the flight models based on system identification once you have flight tests. But you can also use subscale models as have been widely used, and then do system identification, and then use fruit scaling to take these models to a full-scale prediction and use those for updating your physics-based models and developing stitch models. So Cipher is one tool. As I mentioned, there's FitLab, and there are others that have, based on our work, have developed other tools using the same approach. And it is a worldwide standard, the frequency response method. And the multi-objective optimization, which is published in our book and used in Conduit, is also used in other tools. But for rotorcraft, I do believe that Cipher and Conduit should be adopted as worldwide standards because of their widespread use on rotorcraft and validation with rotorcraft flight testing.
All right, great. So let me just reiterate that we are moderating questions for the Nikolsky lecture, and you're very welcome to join in this conversation by typing your questions into the YouTube chat window. If you would please preface your question with a capital Q at the beginning of your question. So let's move on to the next question here. What is the role of variable stability / in-flight simulator rotorcraft like Rascal in the development of future rotorcraft dynamics and control?
So that's a great question, and there are very few number of such in-flight simulators. Rascal is a fly-by-wire UH-60 developed by collaboration between the Army and Boeing, and is invaluable, as well as the in-flight simulator that based on the Bell 214. Sorry, based on the it's left my mind, but they're advanced in-flight simulator, and there are also advanced in-flight simulation in Germany and in Japan, and these are critical. This is the way that you do risk reduction at full scale, and I also think that fixed wing in-flight simulation, for example, the F-16 AFD and the other in-flight fixed wing in-flight simulations developed by Calspan and the Air Force have a role to play, because again, for these advanced configurations at high speed, the rotorcraft really has dynamics which mirror those of fixed wing, and so they have all the same flight dynamics and control issues of fixed wing, and the same kind of characteristics. So those in the community, things like T theta 1 and T theta 2 and so forth for the pitch response. All these things exist in rotorcraft at high speed, and so the in-flight simulation, both rotorcraft and fixed wing from around the world, can and does play a very large role in risk reduction. It was used, as I mentioned, very extensively on the Sikorsky 53K, as well as on many fixed wing programs on the European in-flight simulator, at the fixed wing in-flight simulator at the at Delft, for example, many flight control systems were developed for fixed wing. So there's a very strong role to play, and the Army and Boeing is now developing RASCL 2.0, which will be a state-of-the-art in-flight simulation going forward, and play a very strong role in our research program when that's complete.
Excellent, excellent. The next question comes in particular, given the increasing diversity of rotorcraft configurations, is there a case for a new platform? There seems to be been a decline of research in this area. So is there a case for a new platform?
There are many. If we're talking about operational platforms, I don't think there have ever been a need, especially in the Army. There's ever been a time that we've seen more being developed. This was really a groundbreaking decision by the Army and the Army aeronautics community, and that time led by Dr. Bill Lewis, to develop the JMR tech demonstrators, and now and that technology incorporated into FVL aircraft and a straight line leading to advanced technology for things like UAM and the many eVTOL configurations. So in terms of technology, I think we do have flight demonstrators, but we need flight demonstrators for which the data can be published. And as I mentioned, this is a key challenge. And the DOR, for example, is developing a variable stability coaxial, full-scale coax aircraft based on a full-scale coaxial vehicle. And that's the sort of thing that we need to do in the U.S. and worldwide. We need to have flight validation. In their case, it was an ultralight, and I just want to mention the in-flight simulation at NRC is the Bell 412. That's on my mind. So yes, we need the next generation of in-flight simulation and technology demonstrators. For which we can do parametric studies, and that really doesn't exist in the open literature, and that's something that we need to work on.
Excellent, thank you. The next question comes in, and I know this came in about halfway through. In the cases of extraordinary loading, for example, unbalanced loading or overload, etc., how does the system adapt itself in large helicopters like CH-47?
So in the current aircraft, the loaded configuration is included in the analysis. In the case of conduit, we include it in the optimization. So we typically recommend to design to the nominal configuration, and then look at maximum forward CG and aft CG and loaded configurations as off nominal cases. And so, for example, in the case of Fire Scout, there's a paper by Northrop Grumman and ourselves, Christy Ivler, in which the vertical CG has a significant effect, and you do what's called a multi-model analysis to be sure that each of your off nominal cases stays within bounds. But in some cases, you actually have to design the system and switch it over when you know that you've picked up a load, and you can sense that. So you can have a load limiting control laws or real time knowledge that you picked up a load. So the command KMAX configuration, as I mentioned, uses feedback of the trolley to the control laws. The 53K also uses sling load information in its control law design and development. And so when you have extremely large loads where you have to reconfigure, the stitched model does a great job in reconfiguring for mass configuration, as I showed you earlier. you just need to know the stitch model. You just have a stitched ID model for the nominal loading, and then you can take this off nominal loading configuration, be that external load, CG, or internal load, and then the stitch model updates, and then you can update your optimization, and then you essentially can have a lookup table for these different conditions if you need to, or simply design in the robustness that you need. And that was really the typical approach that was taken in the past. For example, on the legacy CH47, it's a lower gain system, so that when you get to these off nominal conditions, you don't have to change the feedback keys.
Excellent. Yeah, that's good to know. Now we're getting into some more interesting questions here. So
Okay.
there's a statement, then a question. So it says, you've been a mentor to so many engineers over the years, many of whom have gone on to great success in their own right. What is your secret to guiding people to their success?
Wow. So I partly credit that to my father. Again, for each student, I emphasize the need to work hard and push it to the end. And if you see something that doesn't look right, that's a canary in mine shaft telling you something's not right. And many students have enjoyed my hard driving approach. Whether it's working with students late into the night sometimes, or insisting that they use a checklist that I developed for myself when my first paper was being published at STI, and has been used ever since, to work hard and understand the problem, understand the physics behind the problem, and this really takes dedicated effort. And so it's not so much a secret as it follows in the footsteps of many others. That says that the real secret to innovation is 99% perspiration and 1% inspiration, and I believe that's the case. So if there's a secret sauce, that's it. It's work hard, and if you see something that's not right, or go after your first principles, as Professor Pat Curtis always taught me to do. What is the first principle? The students and junior researchers, will say, it's nonlinear effects, it's this or that, and it's generally not. It's generally something first order. And Nerv Ashkenaz at STI taught me that. I was working on an advanced configuration, and he came into the room, and he looked at my calculation of the hydro effect for a new VTail configuration, and he said, it's not right. It looks like it's off. Go back and check your calculations. I said, Irv, you developed 50 aircraft during the war. This is a completely new design. I've checked it. He says, check it again. And I worked on it for about 2 hours, and he came back. He says, well, I said, yeah, I slipped the decimal point. You're right to within 5%. It does match your World War II experience. So you got to stick by your first principles, stick by your guns when you train young engineers, and also give them room to breathe, and give them room to go away, learn on their own. And come back with results. Today there's a tendency for young engineers to share scripts, and this is fine for automated analysis, but it's not a great way to learn the analysis on your own. You really have to generate a lot of these algorithms at least one time in coursework or an application, using a graphical interface which guides you through step by step, or writing the algorithms on your own. To really learn the process. So those are my keys, and the students and young engineers, and I've had many throughout my career benefited and suffered from that bias.
Outstanding. That's great. The reference to Thomas Edison is perfect. I like that. So
Thomas Edison was my father's guiding light. He had a picture of him in his office on the wall, and I also think it really rings true.
It does. It does. So yeah, when I started at GE many years ago, that was the first thing that we learned was a little bit about Mr. Edison himself. Um, so we do have a few more questions, but unfortunately, that is all the time that we have for today. So thank you again, Mark. It was a wonderful and inspiring lecture, and we look forward to many people enjoying it over the next few weeks as we have it on YouTube, and it'll stay there for as long as we can keep it there. And I think that's forever at this point in time with the way the internet works. So, Mark, you will receive your official recognition as part of the 76th annual Grand Awards ceremony, which will also be streamed on this YouTube channel after our half an hour break, and that will start at 2 p.m. Eastern, 11 a.m. Pacific. So, yeah, did you pull up your medal and show it off for us, please?
Yeah, thank you very much. This virtual environment has a number of advantages, and the Vertical Flight Society has done a great job in working through this. This virtual environment allows people from all over the world that may not have otherwise had an opportunity to attend every forum to see these kind of lectures and to attend the forum virtually. So my hat's off to the VFS and the vertical flight community. And again, thank you very much for this wonderful honor. I want to thank especially Dr. Tom Thompson for gathering so many wonderful recommendations from my peers and the community that went into this lectureship. Thank you very much.
Very much. Very well deserved. So at this time, I'd like to thank everyone for watching the 40th annual Nikolsky lecture, sponsored by General Electric. And we hope that everyone will be able to join us for our 76th annual Forum and Technology display, which starts on Monday, October 5th. And you can find more details by going to www.vtol.org/forum, F-O-R-U-M. Thank you very much, and we'll see you back here on this channel at 2 p.m.
Thanks, friends. Thanks very much for joining. Bye-bye.
Bye-bye.